All right, so now we're going to consolidate the understanding of propositional logic that we've achieved so far by formalizing it. So we're going to define the language of propositional logic formally, and then we're going to go ahead and use the definition, which is to say use the formation rules to do what we've done already intuitively, to construct and identify well-formed formulas. And then we're going to introduce two concepts, the concept of scope and the concept of a main operator. Now, these aren't actually discussed in the little book. They are in the larger book, but they're straightforward and we can just deal with them in lecture. All right, so we're going to get a little more formal, explicitly define the language of propositional logic. Now, all languages essentially have two basic elements. We talk about the vocabulary and we talk about the formation rules. So the vocabulary is just a set of symbols, the ones we've already introduced, it turns out, to express the propositions in the language. And you'll note that we're using the term vocabulary technically. When you think of vocabulary, you think of the words you know, but really the vocabulary in propositional logic is more like the alphabet. It's just the basic symbols. And the formation rules are just the rules what we would normally call grammar, or in logic we call it a syntax. The allowable ways of putting the symbols, putting the vocabulary together. Okay, so we already know the vocabulary of propositional logic. First of all, you can use, it consists of capital letters. Now, I haven't mentioned this before. We're also allowed to attach little subscripts if we want to. We hardly ever do, but that guarantees us an infinite supply of symbols, which is kind of a nice idea. Then there's the logical operators, which we've introduced, and then there's the parentheses. Now, these square brackets I've written here aren't really technically allowed. They're not part of the language, but sometimes we just use them informally because formulas get complicated and they get visually sort of hard to see. So they're not really, they're not mentioned in the book as allowable part of the vocabulary, but we might use them sometime. Okay, then there's these formation rules. So there's 4 of them. Well, the last one's kind of funny, but it's necessary. So rule 1 just tells us that any capital sentence letter is a woof. So, P is a woof, Q is a woof, R is a woof. And also that's meant to imply that any capital letter with a subscript after it is also a woof. Now, rule 2 says it uses a Greek symbol phi or phi, and it says if phi is a woof, then tilde or negation phi is a woof. So what that's telling us is that anything that we've already identified as a woof, if we put a negation on the outside of it, that's a woof too. Okay, so if P is a woof, then not P is a woof. And also anything that we've identified as a woof remains a woof if we put a negation on the outside. And then rule 3 tells us, using 2 Greek symbols, phi and psi, if phi and psi are woofs, then all these are woofs too. So again, we're familiar with them. Phi and psi, phi or psi, phi arrow biconditional, if phi then psi, and phi double arrow psi. Now, you might be wondering why we have these Greek letters, they're used in order to have a general way of referring to woofs. And in general, they're used, they're introduced to as ways of legitimately talking about our language. So if I just wrote, if the book just wrote, if P and Q are woofs, well, P and Q are part of the language, so we need a way of talking about the language itself. So we call these terms part of what's called the meta language. The meta language is the logical name, which is a language specifically for talking about language. All right, so Rule 4 says nothing is a woof that cannot be constructed using rules 1 through 3. So essentially that just says, okay, that's it. Rules 1 through 3 are the only ways we can construct woofs. If you can't do it that way, there's no other way. And that's actually one of the rules, though we rarely explicitly appeal to it. Well, we would explicitly appeal to it if we were trying to show that something is not a woof. Okay. All right, so now we'll go ahead and use the formation rules to figure out whether certain things are woofs or not. It's something we've been doing intuitively, and now we'll do it formally, straight up. So in each case, what we're going to do is try to build a particular formula using the formation rules. If we can build it, then it's a woof. If it's not, then we can't. This is what computer scientists call an algorithm. It's a procedure that is guaranteed to produce the result, and what logicians call a proof procedure. Okay, so is this a woof? Well, your intuitions are probably pretty good here. You'll just look at it and say, of course not, there's no brackets. But in order to do this formally, what you'll say is, well, look, Rule 1 tells us that P is a woof. Rule 1 tells us that Q is a woof. Look, there's no rule that allows us just to write the arrow in the middle. You have to add these brackets by Rule 3. So, no, this is not a woof. Is this a woof? Conjunction P, very strange looking, but strange doesn't mean it's not a woof, as we'll see. Rule 1 says P. Can I just add a conjunction on? Well, Rule 2 says I can add a negation, but I can't just add a conjunction. So by Rule 4, which I haven't written up there, these are the only 3 rules I can use, so there is no way to do that. That's not a woof. Is this a woof? Well, we haven't seen this yet. Let's see. P is a woof by Rule 1. Q is a woof by Rule 1. P or Q with brackets is a woof by Rule 3. By Rule 2, I can add a negation. Oh, but by Rule 2, since now this is a woof, by Rule 2, I can add a negation. And since this is now a woof, by Rule 2, I can add a negation. So yeah, that's a woof. Is this a woof? Well, P is a woof. Is it possible to just, well, Q is a woof, right? But is there any way to put P and Q just together like this? No, no rule allows us to do this. So simply setting 2 sentence letters together is not permitted by the rules, so this is not a woof. Is this a woof? This kind of looks like one. let's see. R is a woof by rule 1. Not R is a woof by rule 2. There is no rule that allows me to do this, right? The parentheses are only associated with conjunction, disjunction, conditional, and biconditional. So there is no rule that says this is a woof. You may say, well, why not? I mean, it looks like it's a perfectly legitimate thing to do. Well, it just isn't. We don't write formulas like that. It's just not part of the grammar. So that's not a woof. Oh, that's my dog. One of them. Okay, P and S then R. You can see that's not a woof. Well, prove it. Look, P is a woof. S is a woof by rule 1. P and S are woofs by rule 3. R is a woof, but P and S then R is not a woof, right? Because we have to add brackets on the outside. So this would not be a woof. Is this a woof? Well, hopefully you can see that we're kind of repeating what we did before, but what's the full proof? R is a woof. R is a woof. Not R is a woof by rule 2. This is not a woof, right? No, that's not permitted. That's not permitted. That's not a woof. P is a woof. Q is a woof. Is this a woof? Is this a woof? Nope. There's no rule that permits either of those. Not a woof. Getting the idea? Sure. Okay, is this a woof? First blush, it looks kind of like it might be, but you can probably see a little problem. So, okay, P is a woof. S is a woof. Is there anything that allows us to put not and, oops, get a little better there. Eraser. Not and. Now there's no such thing as not and. So that's not one of the and, or, if then, if and only if. Not and is not one of our connectives. It'd be kind of an interesting connective, but we don't own it, so that's not a woof. Is that a woof? That is truly bizarre looking. But look, P is a woof. Q45 is a woof. Because 45 is just a subscript. We didn't put any limit on the number of subscript, the size of the subscript you could write. Is not P a woof? Well, yeah. Is not P a woof? Well, yeah. I'm not going to keep going, right? You get the idea. Dot, 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 until you get to this, right? And then, or brackets. So yes, this is a woof. Is this a woof? Q and R subscript 7. Q, okay. R, okay. Rule 1 woofs. And R with parentheses, rule 3 woofs. Is there anything that allows us to write a subscript here? No, there is not. Now, this is not actually necessarily evident from here, because this says any capital sentence letter is a WOOF, and really the expanded version of this, any capital sentence letter or sentence letter with subscript. So Rule 1 allows you to put subscripts on the capital letters, but there is no rule. Rule 3, for example, does not allow you to put subscripts on the outside of parentheses. So this is not a WOOF. Okay, well, let's finish up by talking about the idea of a scope and the idea of a main operator. As I mentioned, these concepts are not discussed in the little book, but they're mentioned briefly in the larger book in section 3.3 actually, and we'll cover it just as much detail here as it is in that book. So sometimes we speak of the scope of an operator. It's the operator that has scope. So the scope of an operator in a WOOF is the operator itself and the subwoofs to which the operator directly applies. So if I'm just going to write down a random WOOF, say P and Q, if and only if that's ugly. If and only if R or S, then T. One, two, three, four, five, six, 7, 8, right? Okay, now I can ask about the scope of each of these operators. There's 1, 2, 3, 4 different operators. And what this says is that the scope of an operator in a WOOF is the operator itself and the two subwoofs, the tiny woofs, to which the operator directly applies. So the scope of and joins P and Q. The scope of and is actually the operator and the connective. So the scope of and is P and Q. The scope of the conditional over here is the conditional and these two formulas that it connects. So the scope of the conditional is R or S, then T. That's the scope of the conditional. Now the scope of the biconditional is the two formulas that it connects, and that is this formula and the biconditional. So the scope of the biconditional is actually the whole formula. And so we call the biconditional the main connective or main operator. Okay, which is what I go on to say here. So actually there's another way of saying what the scope of an operator is, and this is that the scope of an operator in a WOOF is the smallest subwoof that contains the operator. So we didn't ask about the scope of the wedge, of the disjunction. What's the scope of the disjunction? Well, you could say, what's the smallest subwoof that contains the operator? Smallest subwoof that contains the operator is that. Okay? So the main operator, sometimes I say connective, as you know, the main operator is just the operator with the largest scope, which means that it's the operator for which the smallest woof that contains it actually turns out to be the entire formula. So if and only if here is the main operator because the smallest woof that contains this operator is the entire formula. Okay. Okay, so let's just do a little more scope identification. Let's identify the scope of each of these connectives. All right, so go ahead and, as you should be doing all the time now, go ahead and pause whenever I ask you and see if you can figure it out. What's the scope of the conjunction and? All right, what's the smallest formula, the smallest subwoof that contains and? Well, that would be S and P1, right? So that is the S and P1 is the scope of and. What's the scope of the negation? Well, the smallest formula that contains the negation is not S and P1. Whoops. Right? What's the scope of the disjunction? Smallest formula that contains the disjunction is Q or R. So that's the scope of the disjunction. Scope of this conjunction. Well, before we ask that, what's the scope of this negation? Well, smallest formula that contains it, subformula that contains that is not P. What's the scope of this conjunction? Well, smallest formula, not P and Q or R. Finally, what's the scope of this negation? Scope of this negation, the smallest formula, subformula that contains this negation is the entire formula. So what's the main connective? The main connective is the negation. Right? Main connective is the negation. The outside negation. Okay. So let's identify some main connectives. Could it be the conjunction? Well, no, it can't be because P and Q contains the conjunction. So here it's the negation. Could it be the negation? No. Smallest formula that contains the negation is this. So here it's the conditional. Smallest formula that contains the or is Q or R. Smallest formula that contains the negation is not P. So here it's and. Smallest formula that contains the biconditional is not P if and only if not P. So here the main connective is or. What's the main connective here? Well, obviously it's a negation, but which one? Well, it's got to be the one on the furthest outside, right? Because it can't be this one, because the smallest one that contains this negation, the first negation, is not P, right? So it has to be this one. And then finally, what's the main connective here? Well, this is pretty big. We can see it's not this conditional because that links these two formulas together. We can see it's not this conditional because that links these formulas. Actually, it links these formulas together, right? So it has to be, oh, excuse me, it links, I said that incorrectly. The biconditional links these formulas together. This negation applies to this formula, And so it's the biconditional that holds the whole formula together. So it's the biconditional that's the main operator here. Okay? So let's do some quick study questions. Some of these are all multiple choice, so these don't, they don't give you a great sense of how you're doing. It's much more important to be able to produce than to choose, but there'll be a sort of a small test of your comprehension. That's what would make it a woof, right? Oops, that was the same one, wasn't it? Oh well.